So in this last segment, we're going to take a look at one more example, then talk about ways we can improve reliability. In this particular circuit, what we have is we have a very simple type of system where we have a 3-mile long main feeder, and we have 2 taps that are half a mile long each. And tap 1 has 800 customers and tap 2 has 400 customers. So have more customers on the source side of the circuit than we do towards the end of the circuit. And what we're going to consider is we're going to consider the addition of switches and see what the impact on reliability is going to be in this case. So as far as the information we're going to be working with, as far as the parameters, then we've got a failure rate, a permanent failure rate of 0.5 failures per year per mile for the main feeder and 1 failure per year per mile for the tap or the laterals. The reason being is we typically would do more maintenance on the main feeder than we would on the taps, because the mains would have more impact on customer reliability. We're not going to consider temporary faults in this case. We're mostly interested in looking at SAIDI and SAIFI numbers. And so we're just going to be focusing on the permanent faults. And the mean time to repair is assumed to be 4 hours. So first thing we need to do is we need to do a baseline, and then we're going to add a midpoint switch, and then we're going to add a backfeed switch. And when we have the midpoint switch, this has a 1 hour switch time. When we're going to add the backfeed switch, what we're going to assume is that's going to add an additional 0.5 hours to operate the backfeed switch. So for the pair, that'll be 1.5 hours. So if we use our approach that we talked about in the previous examples, we basically have 3 contingency locations. We have faults in the main feeder, we have faults on this first tap for customer A, and we have faults on the second tap for customer B. And so what we can do in this case is we multiply the failure rate times the line miles. That'll give us the number of events per year in this case. And so this is always kind of a good starting point, would be to identify again where are the contingencies that we need to consider for doing this analysis. Now, what I've done is I've used the same contingency table as before, but what I've done is I put some of my statistics in the table. It just makes it a little bit easier to do the bookkeeping. And so the part on the right is the same as what I had before, but then I've added some of the parameters in the table. So if I were going to maybe update some of the parameters, I could see right away what the impact on reliability is going to be. And so you do exactly the same sort of thing we did before, where you look at the number of events per contingency. And so for this first segment, what I'm going to have is I have a failure rate of 0.5 failures per year per mile. I multiply that by the 3 miles, and that's going to give me a number of failures of 1.5 per year. Okay. So what happens if I have a failure on the main feeder? Well, what that's going to do is that's going to result in the circuit breaker operation. Since it's a permanent fault, eventually it's going to have to lock out. There's no fuses involved. And for each customer, if I have 1.5 of these events per year, this is 1.5, a 4-hour mean time to repair, then 1.5 times 4 gives me 6 outage hours. And so this is how we would fill this table out. If we're talking about an event on a tap or a lateral, let's say for customer A, then if we have a failure rate of 1 per year per mile, if I've got 0.5 miles, multiply 1 times 0.5, and that's going to give me 0.5 of these events per year. We would not have a lockout for the circuit breaker in this case, so the fuse is eventually going to blow. So we're going to have 0.5 fuse operations per year. And then if we're going to have 0.5 of these events per year per customer A, then if it takes like 4 hours to fix, then 0.5 times 4 hours is 2 hours. Note that a fault on lateral A does not impact the customers at B and vice versa. And so if you do all this number crunching and you put this stuff in the table, you can get the net sustained outages for each customer. You can get the total outage hours. And what we end up with in this case is we end up with an average interruption frequency index of 2 interruptions per year. And for outage hours, we end up with the SAIDI number of 8 hours per year. So this is, I guess you can think about this as a base case that we're going to be using for comparison. So now what we're going to do is we're going to add a switch. In this case, we're going to assume it's going to be a manual switch. Later on, when we talk about feeder automation, we'll look at different sort of automated switch options. But in this case, let's just assume it's a manual switch. And so what this manual switch does is we're putting this right in the middle of the main feeder. So this is bisecting the feeder. So we have 2 segments of 1.5 miles. And instead of having a single contingency in the main feeder, we have a contingency between the circuit breaker and the switch, and we have a contingency below the switch. So now we have a total of 4 different contingencies where the time to do the switching operation on the switch is going to be 1 hour. For the circuit breaker, what we're going to be assuming in this case is the station breaker's circuit breaker can be operated by SCADA. That means we have remote control. And so for what we can assume in this case is we can assume that the operation time for the SCADA is negligible because an operator is going to reclose. So I've got 4 contingencies. I can go ahead and set my table up and I can go through and I can do the same type of analysis. Nothing changes on the laterals, but what changes is what happens on the main feeder. And so what's going to happen if I have a fault on the top of the main feeder is I get the same results as before, because if I have this fault on the top of the main feeder, I have no backfeed for customer B. And so both customer A and customer B are going to be out. So I'd get the same result that I would have in the base case. But if I have a fault on the bottom of the main feeder, okay, I'm going to have a failure rate of 0.5 failures per year per mile. I've got a total of 1.5 miles. That gives me a total number of these events of 0.75 per year. So you see this doesn't have to be an integer. This is going to result in a circuit breaker lockout. And then what's going to happen is I'm going to operate that switch. And so this switching operation is going to occur 0.75 times per year. And if the count for customer A is going to be 0.75, then when that happens, it only takes 1 hour basically to go to the switch location, open up the switch, and then the operators are going to close via SCADA the circuit breaker. And so this only takes 1 hour to restore customers at location A. And so then if I take the count and multiply by mean time to switch of 1 hour, then that gives me an outage hour of 0.75. The customers at location B, they still have a mean time to repair 4 they have to live with. So 0.75 times 4 gives me 3, right? So this is how you would update the numbers. And then what you can do is calculate a new SAIFI value. And so what we're going to see in this case is for customers at location A, then what they're going to see is they're going to see 0.75 events at the main feeder top, 0.75 events in the main feeder bottom, 0.5 events on the lateral. We got a similar set of numbers for customers at B, and you can see we're still at 2 interruptions per year. So we still have the same SAIFI number. But what's going to change in this case is because we have the isolation switch, we don't have to have customers at a point, wait for that second segment to get fixed. We just simply do a switching operation, and instead of this being a 3 hours, they're back in 0.75 hours. So then what this does is this drops the SAIDI value down to 6.5. So what we've done is we've gone, if you look at the base case, SAIFI 2, SAIDI 8. SAIFI still 2, but SAIDI dropped down to 6.5. And so if you were going to do some economical analysis on the circuit, then you might have a certain value of reducing the SAIDI index. And then you can kind of figure out for X number of customers what it would be worth from a reliability improvement standpoint. And you can compare that to the cost of installing the switch. So finally, you've got a case, we're going to add now this tie switch. This doesn't change the contingencies any, but what it changes is what we can do for customers at B if we have a fault on the top section. And we'll assume in this case that mean time to switch adds another half hour to the switching. So for the net pair, we've got 1.5 hours. All right. So what changes in the table now is if you look at an event on main feed or top, the customers at A still have to wait 4 hours. So this outage hours is still 3. But what's going to happen now is we're going to get a switch operation. We're going to be able to isolate those customers that are on the bottom half of the circuit. You know, we're going to be able to disconnect them from the original source, connect them up to a backfeed source. That's going to take a total of 1.5 hours. And so if you take if you take this count of 0.75 and you multiply that by the switching time, the net switching time of 1.5, then you get 1.125 outage hours now. So when you go through and you update your SAIFI and SAIDI numbers, you still have 2 interruptions per year. So until we get to the fast switching through automation, we're still going to keep the SAIFI number basically the same. But what this does is it drops the SAIDI number down a little bit. So if you compare this to the previous case, we're at 6.5. You add one more switch and we go down to 5.875. So it doesn't really seem like much of an improvement for putting that switch in. And what you would have to consider, you know, would be what's the cost of the switch, obviously, and what's the value of reliability. And where the business case gets better for this is it gets better if there's customers at location B that require higher power quality. So there's a school or a hospital or whatever, that might kind of help the business case as far as getting the switch in. The other thing you need to consider too is not all loads have potential backfeed sources. There could be loads on feeders out in the middle of nowhere and there's just no backfeed. And so there's just nothing you can do as far as a backfeed. But anyway, this just kind of shows some basic calculations, and what you would do as a reliability engineer is once you do these calculations, then you basically would look at, well, what's the incremental improvement you get with respect to the cost of the upgrade you'd have to make. And then if you have a dollar number for reliability, and if you can convert the cost of installing the switch to some value that's comparable, then you can compare those two numbers and you can figure out whether it's worthwhile doing this project or not. So utilities would have thousands of these projects as possibilities, and what they would do, given their budget, they rank the projects, and then they would start funding the projects according to their ranking. So just to summarize, what are different ways we can improve reliability? So if you were a distribution planner and you were needing to improve reliability, what could you do? The first thing would be just find ways of reducing the failure rate. And so if you look at your equipment, you may replace equipment or do maintenance on equipment just to reduce the failure rate. The other thing you can do is more from the protection side, is you would improve on the protection selectivity. And so what this means is you create more zones. So when a fault would occur, you basically would isolate the fault into a smaller area in a smaller zone. And then you could also have more switches out there to kind of complement that. You could certainly have more backfeed paths, and some utilities have a little bit more rigorous approach, as far as making sure there's always backfeed paths. And then the other topic would be to automate your switching. This is a topic we'll just have a separate lecture on later, where we talk about automated fault location isolation and service restoration. And so first you have to know where the fault's at. Then after the fault occurs, you need to be able to isolate it from the rest of the feeder. And then you would have to have ways of restoring load and through switching and then repairing the fault. And so all those different steps we'll talk about later in a future lecture is what we refer to as FLISR. Different utilities would have different names for this. So I'm not going to get into that right now, though. So as far as minimizing the number of failures, tree trimming is one. Use of covered wire where you don't get branches hitting the wire and causing short circuits because now the wire could be insulated. Inspecting your feeders, replacing overhead wire, replacing underground cable that's going bad, improving lightning protection, making sure you don't overload your transformers, and monitoring your substation transformer. So if there's some damage, you can try to address the damage before you have a complete substation transformer failure. So these are just all sorts of different things you can do. Just getting into a little bit more detail on some of these. For tree trimming, you'll probably go down the street and you see trees are pretty close to your power lines. And so this just kind of shows different sort of trimming strategies, like you got side trimming where you're trimming one side of a tree to keep it clear of the line. You've got through and under trimming where maybe this is where the wire is at. You've got topping which is a more aggressive type of trimming. There's all sorts of different ways you can actually trim trees. And what utilities will do is they'll typically have a cycle where they'll trim the trees along a feeder segment maybe every 3, 4, 5 years, something like that. So after you do tree trimming, then what starts to happen is that as the trees grow back, then the failure rate just starts to creep up, right? And then year by year, it gets worse and it changes, right? Until at some point, it just gets really, really bad. And so if you were to do tree trimming, then what you would expect is the failure rate starts to get bad. You trim the trees, it goes back down. Trees go back into the wires. You do trimming again, it goes back down. You kind of see this sawtooth effect as far as how the failure rate changes on sections of circuit that are trimmed. But this obviously costs a lot of money, and if you can figure out a way of optimizing your trim cycles, you could save your company a lot of money. Cable replacement, cables get old, they get damaged due to over voltages or getting moisture in the cables. There's actually different ways utilities can test their cables to see what the remaining life is. And so basically, if you apply a voltage impulse, you can see how the insulation responds. Partial discharge is looking for the beginnings of a failure. You can take measurements and look at things like power factor, because if the power factor starts to change, and that's sort of indication of the dielectric starting to go bad. And so there's a lot of different things you can do as far as cable and doing some sort of periodic inspection of your cables. You probably wouldn't likely do a lot of this stuff though, unless you were kind of suspecting that certain sections of cables were going bad. And so if you had brand new cable, you wouldn't be doing this, but as the cable starts to age, you would probably do this more periodic inspection and try to be a little proactive as far as identifying possible problems instead of waiting until the faults occur and the customers complain. We talked about use of switching, putting out more fuses on laterals and basically putting fuses in series, using reclosers to kind of sectionalize circuits, or putting manual switches out there are all kind of valid options. Probably putting out these switches, would have quite a bit of bang for the buck as far as they're not really expensive, and it gives you a lot of flexibility for reconfiguring the circuit. So anyway, they're slow. It would maybe take an hour to get there, but you're going to have a lot of these manual switches out there. And if you're driving around NC State campus, I mean, you'll actually see a lot of locations where we've got these switches that are ready to be operated as needed. As far as location for these switches, you can do this through reliability analysis, and usually it turns out that good locations for these switches are points where you have load that you want to kind of protect from poor reliability. So let's suppose you've got a section of circuit and you got different loads on here, and you've got a lot of customers at location B and maybe not so many customers at location C. This would probably be a good location for a switch right here. All right, so generally we're going to find these switches are pretty close to large customer pockets or critical customers, because you want the flexibility of restoring those customers more quickly. So it's not going to have the impact on SAIFI. You're not going to be changing the frequency of the interruptions, but you'll be cutting down on the net outage hours. And then if you had a no tie switch, if you can put like a backfeed tie switch in here, that would help as well. We talked about the fact that you can put more protection devices out in the circuit. So a very common thing to do, if I had a long feeder, would be you bisect it with a recloser. This is usually the start of an automation program. If you had like branches, that might be one place to put more reclosers at. If you had like long laterals, you could maybe use fuses in series and break the lateral into segments and things like that. And so there's things you can do with adding more protection devices if you're careful. One thing about putting devices out there is you need to make sure, if you have three-phase loads, that when you have an operation of protection, it does a three-phase operation generally. And the reason for this is a lot of loads have motors, and motors don't like unbalanced voltage where you have voltage on two phases and not the third. So generally you want to have ganged operation of protection above large motors. So here's an example. If we had like a substation that had reclosing capability, if I get to like a Y section, I might want to have reclosers in here that kind of break this apart. Not only does it make it easier for me to see a fault way at the end of the circuit when we talk about sensitivity, but it also kind of breaks things down as far as managing reliability, where if I have a fault here versus a fault here, I'm not taking too many customers out. I'm kind of limiting to a certain area. You can have multiple reclosers in series. One thing you have to watch out for is you can only have so many reclosers in series and still be able to coordinate. And so if these reclosers are too close together, you can't really coordinate the operation of reclosers that readily. And then this just shows an example where I have a lateral and I break it into like a lateral and a sublateral through the use of fuses. And again, what you have to watch out for is whether these two fuses in series can actually coordinate or not. And we talked about fuse savings as well. And so reclosers were developed to be able to deal with temporary faults. And a lot of faults are actually going to be temporary in nature. And so as far as the applications, just some things we have to watch out for is first of all, I can get fuse savings to work in situations where I have like overhead, because overheads, typically the faults in them are a lot of times self-clearing. So if I want to go ahead and put a slow fuse in here, and if I'm looking at having like a temporary fault here, I can a lot of times clear that through the local recloser. But if you're up close to the top of the substation, then these fault currents are so high, maybe like over 5,000 amps, that fuse savings is not possible, because you get that much current flowing through that fuse for any small length of time, that fuse is going to pop right away. And so fuse savings is sometimes kind of difficult to do at the top of the feeder. And a lot of times what we do at the top of the feeder, we put fast fuses in here because we know we can't coordinate. So you're better off just clearing the fault as fast as possible and trying to prevent an operation of the recloser. Now, another place where you don't want fuse savings is where you have underground cable. So for underground, what we're going to want to do, if we have a fault in underground, that's typically always a permanent fault. So there's no sense trying to even do fuse savings. And so what we would do here is we put a very fast fuse. So if any fault would occur, that would clear very, very quickly. Because the faster we can clear that fault, the less damage we're going to have for that cable. So anyway, there's a lot of different things you can do for reliability, and a good reference that you ought to look at if you want to get more information on this is the book by Richard Brown. He has a whole textbook on this, and what I've basically been kind of covering is some of this material on component modeling and how we do the system modeling and the calculations in the system analysis. Another book that gets into I guess talking about reliability in general, maybe not the analysis, but kind of talking about what drives it, is the book by Tom Short. And when he was at Electric Power Research Institute, he was involved in a lot of different studies on reliability. Okay, so anyway, hopefully, this is enough to kind of get you started on reliability, and we'll have like a few homework problems on this as well. Okay, thank you.